The ground explodes. Mountains shake. Armies scream and empires erase themselves from history. And yet, this wall is still here. For over 2,000 years, earthquakes tried to snap it, invaders tried to burn it, and time tried to forget it, and failed. This is history of questions, and today we're asking the impossible. How did the Great Wall of China survive centuries of pure chaos? From a structural engineering standpoint, the survival of the Great Wall of China defies almost every known rule of ancient construction. The wall stretches over 21,000 kilometers, crossing deserts, mountains, floodplains, and major seismic zones, a scale that dramatically increases structural vulnerability. Many surviving sections stand 6 to 8 meters high, with base widths ranging from 5 to 7 meters, tapering to about 4 to 5 meters at the top, dimensions that create enormous weight loads. Without steel reinforcement, deep concrete foundations, or expansion joints, such mass should have produced fatal stress fractures over time. Modern engineers know that long rigid structures without flexibility are especially prone to collapse during earthquakes. By those standards alone, large portions of the wall should have failed within the first few centuries. Early sections of the wall were built primarily using rammed earth, a technique involving layers of soil, sand, gravel, and sometimes reeds compacted between wooden frames. Each compacted layer averaged 10 to 15 centimeters thick, creating dense, laminated walls that could reach several meters in height. While rammed earth erodes easily under rain, its internal structure allows slight compression rather than sudden fracture during seismic activity. Unlike stone blocks that crack when stress exceeds tolerance, rammed earth redistributes force across layers. This meant early walls could partially deform during earthquakes instead of collapsing outright. From a seismic perspective, this accidental flexibility dramatically increased survival odds. Foundations further defy modern expectations of stability. Many sections rest directly on compacted soil or carved bedrock rather than deep footings. In mountainous regions, builders embedded walls directly into ridgelines, using natural rock as structural anchors. Where foundations existed, they were often less than 1 meter deep, extremely shallow by modern seismic standards. However, uneven terrain disrupted seismic wave transmission. This prevented synchronized movement that could have caused large-scale collapse. The wall's length alone should have ensured its destruction. Long structures are especially vulnerable to thermal expansion, ground displacement, and fault movement. The Great Wall crosses active systems like the Shaanxi Rift Zone, which experienced earthquakes exceeding magnitude 7 multiple times in recorded history. Unreinforced masonry buildings often collapse completely under such forces. Instead, damage to the wall remained localized to specific segments. This fragmentation prevented total structural failure across its full length. Human activity posed an equal threat to the wall's survival. Over centuries, nearby populations dismantled sections for bricks, roads, and farmland. Defensive walls elsewhere collapsed rapidly once stripped of outer layers. Yet many wall segments retained thick internal cores even after surface materials were removed. Bases measuring around 5 meters wide allowed sections to remain standing despite heavy looting. The wall's mass created structural redundancy long before the concept was understood. The wall ultimately survived because it evolved through repeated failure. Weak designs collapsed early and were abandoned rather than preserved. Stronger techniques were copied, refined, and expanded by later dynasties. Ming engineers standardized bricks at roughly 40 by 20 by 10 centimeters, improving load distribution and repair efficiency. Repairs focused on modular replacement rather than total reconstruction. Over centuries, the wall became an adaptive system instead of a static monument. After understanding that the Great Wall of China was never expected to endure for millennia, the next question becomes how it repeatedly avoided total collapse. Earthquakes do not destroy structures simply because they are old, but because they are too rigid to handle sudden movement. Much of the Great Wall avoided this fate because its primary materials allowed controlled deformation. Early rammed earth sections could tolerate 0.3 to 0.5% strain before cracking, far exceeding unreinforced stone. This meant seismic energy dispersed through compression instead of concentrating at fracture points. Survival came from movement, not resistance. That flexibility was made possible by the wall's layered internal structure. Builders compacted soil, gravel, sand, and plant fibers in 10 to 15 centimeters thick layers, forming laminated cores. Each layer interrupted crack propagation, preventing fractures from spreading unchecked. In unlayered masonry, a single crack often leads to rapid failure. Organic additives such as reeds and straw increased tensile strength, acting like primitive reinforcement. These layers turned seismic shock into manageable internal movement. Because layers alone were not enough, wall proportions reinforced this bending behavior. Many surviving segments maintain a height-to-base ratio close to 1:1, such as 7 meters tall with bases 6 to 7 meters wide. This geometry lowered the center of gravity and reduced overturning during lateral acceleration. Narrower walls nearby collapsed more easily under similar conditions. Wide bases absorbed energy by spreading force downward into the ground. Stability emerged from mass distribution rather than material strength. Even with stable proportions, uninterrupted length would have caused disaster, which is why segmentation mattered. The wall was constructed as discrete sections divided by terrain changes, gates, and watchtowers spaced roughly every 100 to 200 meters. These breaks functioned as stress buffers, limiting force transfer during earthquakes. When one segment cracked or collapsed, adjacent sections often remained intact. This prevented domino-style destruction across long distances. Fragmentation preserved continuity. Segmentation worked best because it was paired with terrain-aware construction. Walls placed along ridges and uneven slopes experienced lower horizontal acceleration than those on flat plains. Geological studies show rocky ridgelines reduce seismic amplification compared to alluvial soils. In mountainous areas, walls were anchored directly into bedrock, limiting sliding and rotation. Uneven ground disrupted seismic wave coherence before it reached the structure. The landscape itself became part of the shock absorption system. Over centuries, repeated earthquakes refined every one of these features. Northern China experienced dozens of major seismic events, including earthquakes estimated between magnitudes 7 and 8 along wall regions. Each event destroyed weaker configurations and spared stronger ones. Later dynasties rebuilt using the designs that survived, unintentionally conducting long-term seismic testing. Flexibility, layering, segmentation, and terrain integration became dominant because they worked. The wall survived not by defying earthquakes, but by learning from them. After flexibility and segmentation kept the wall from collapsing outright, long-term survival depended on whether its materials could resist decay. During the Ming Dynasty, builders introduced a lime mortar mixed with sticky rice soup, a decision that permanently changed the wall's durability. Chemical analysis shows this mortar formed calcium carbonate amylopectin complexes, creating bonds stronger than lime alone. Compression tests on surviving samples demonstrate up to 2-3 times greater shear strength than conventional ancient mortar. The mixture also drastically reduced water penetration, slowing erosion from rain and freeze-thaw cycles. This upgrade transformed vulnerable brick sections into long-lasting infrastructure. Water is one of the most destructive forces acting on ancient structures, especially after earthquakes create microcracks. Standard lime mortar dissolves slowly under repeated moisture exposure, weakening joints over decades. Sticky rice mortar reduced porosity by over 30%, according to modern materials testing. This limited internal water expansion during freezing temperatures, a common cause of masonry failure. By keeping bricks tightly bonded, the mortar prevented seismic cracks from widening over time. Earthquakes damaged the wall, but water was no longer able to finish the job. Sticky rice mortar also solved a critical maintenance problem: repair speed. Ming bricks were standardized at roughly 40 by 20 by 10 centimeters, allowing damaged sections to be replaced quickly. Mortar cured rapidly while maintaining flexibility, meaning repairs could be completed between military threats or after earthquakes. Faster repairs reduced the time cracks were exposed to erosion. This turned the wall into a maintainable system, not a static monument. Longevity came from repeatability, not perfection. The chemistry behind sticky rice mortar explains why Ming sections survive far better than earlier walls. Many pre-Ming earthen walls eroded within centuries once maintenance stopped. In contrast, Ming brick sections remain intact even after 600+ years of exposure. Scientific studies confirm that organic-inorganic bonding slowed structural fatigue. This was not magic or myth, but accidental biochemical engineering. Food became infrastructure. Sticky rice mortar also resisted seismic vibration better than brittle alternatives. Its slight elasticity allowed joints to absorb micromovements during tremors instead of snapping. Tests show improved energy dissipation compared to pure lime mortar. This meant earthquakes caused localized damage rather than cascading failure. The wall could crack without falling apart. Survival depended on controlled weakness. By combining flexible materials with advanced mortar, the wall crossed a threshold from ancient to proto-modern engineering. Sticky rice cement did not make the wall indestructible, but it made damage manageable. It slowed decay, improved repair cycles, and stabilized seismic fractures. Without this innovation, large portions of the wall would have vanished centuries ago. What looks like simple brickwork is actually layered chemistry in disguise. This was survival through science, long before science had a name. After material flexibility and advanced mortar stabilized the wall itself, survival increasingly depended on where the wall was placed. The Great Wall of China was deliberately routed along mountain ridges, steep slopes, and rocky spines rather than flat plains. In northern China, ridgetop ground can reduce seismic amplification by 30 to 50% compared to soft alluvial soil. Earthquake waves lose coherence when they pass through uneven terrain, lowering peak horizontal acceleration. Builders did not calculate wave physics, but they observed which locations survived shaking. Geography filtered destruction before it ever reached the wall. Mountain foundations changed how force entered the structure. In many regions, walls were built directly onto exposed bedrock rather than soil. Bedrock reduces differential settlement, one of the main causes of cracking during earthquakes. Geological surveys show that bedrock sites can experience up to 60% less ground displacement than nearby sediment-filled valleys. By anchoring walls into rock, builders limited sliding and rotation during tremors. The mountain became a natural foundation slab. Elevation also reduced environmental decay. Mountain ridges experience faster drainage, preventing prolonged water saturation after rain or snow. On flat land, trapped moisture accelerates erosion and freeze-thaw cracking, especially after earthquakes open microfractures. Elevated sections dried faster, preserving mortar integrity and brick cohesion. This reduced long-term weakening between seismic events. Earthquakes cracked walls, but mountains prevented slow rot from finishing the damage. Mountains also limited the scale of collapse. Steep slopes naturally segmented construction, forcing breaks, turns, and elevation changes every few hundred meters. These terrain-driven interruptions acted like seismic isolation zones. When one segment failed, the slope often prevented force transfer to the next section. This reduced cascading collapse along long stretches. Geography enforced segmentation even where builders did not. Mountains also protected the wall from direct assault. Siege equipment, large formations, and sustained battering were nearly impossible on narrow ridgelines. Invaders focused on passes and gates rather than dismantling walls perched above them. Because attackers rarely destroyed mountain sections, these areas suffered less structural damage over centuries. Reduced warfare damage meant fewer weak points for earthquakes to exploit later. Geography shielded the wall from both enemies and physics. Over time, builders learned which landscapes preserved walls best. Sections on plains eroded or collapsed faster, while mountain sections endured. Later dynasties increasingly prioritized ridges, cliffs, and rocky spines when rebuilding or extending the wall. This selective survival shaped the wall's modern footprint. What remains today is not random, it is geography-tested. The mountains did not just support the wall, they chose which parts would live. After geography absorbed much of the physical punishment, survival depended on organization. The Great Wall of China was never a single continuous barrier but a distributed military system spread across terrain. Watchtowers were typically spaced 100 to 200 meters apart, allowing overlapping visibility and rapid response. Beacon towers relayed signals using smoke by day and fire by night, transmitting alerts over hundreds of kilometers within hours. Garrison forts housed soldiers, supplies, and repair crews close to vulnerable sections. When earthquakes or attacks damaged one segment, the system rerouted defense and maintenance elsewhere instead of collapsing as a whole. This networked design limited the impact of invasions. Historical records show that many invading forces bypassed intact wall sections to target passes, gates, or internal cities instead. Because attackers sought speed and supply lines, dismantling thick walls offered little tactical reward. Even when gates fell, adjacent towers and forts continued functioning independently. This prevented wholesale destruction of the wall during military campaigns. The system absorbed breaches without failing entirely. Redundancy also protected the wall from earthquakes. Each watchtower and fort functioned as a structural break, limiting how seismic stress traveled. Towers acted as mass dampers, absorbing motion differently from long wall stretches. When tremors cracked one segment, adjacent towers often remained stable. This compartmentalization mirrors modern seismic zoning in large infrastructure. Damage stayed local because the system was intentionally fragmented. Logistics turned damage into delay instead of disaster. Many forts stored months of grain, tools, and spare bricks, enabling rapid post-earthquake repair. Ming-era military records describe repair crews dispatched within days of major damage. Standardized bricks and mortar allowed modular replacement rather than full reconstruction. This kept weaknesses from compounding over time. Maintenance was continuous, not reactive. Communication speed mattered as much as strength. Beacon systems could relay a warning up to 500 kilometers in a single day under clear conditions. This allowed commanders to concentrate forces and resources where damage occurred. Fast response reduced the window in which cracks could widen or enemies exploit gaps. The wall survived because information moved faster than destruction. Coordination turned vulnerability into control. Over centuries, this system proved more durable than any single wall design. Sections collapsed, towers burned, and gates fell, yet the network persisted. Later dynasties rebuilt nodes rather than entire stretches, preserving function even amid ruin. What survives today is the residue of a resilient system, not a flawless structure. The Great Wall endured because it behaved like infrastructure, not a monument. After functioning as a resilient system, the Great Wall of China survived because it was never treated as finished. Across more than 20 centuries, at least 7 major dynasties repaired, expanded, or rebuilt sections of the wall. Earthquakes, erosion, and warfare routinely damaged long stretches, but abandonment was rare. Instead, rulers treated collapse as feedback rather than failure. Weak sections were rerouted, reinforced, or replaced with better designs. The wall endured because it was continuously re-engineered. Rebuilding was not random. It followed patterns learned through destruction. Early earthen walls that eroded quickly were replaced with stone or brick in high-stress regions. In flood-prone or seismic areas, later dynasties widened bases and reduced height to improve stability. Archaeological surveys show Ming reconstructions often increased base width by 20 to 30% compared to earlier designs. Each rebuild encoded lessons learned from previous failures. The wall evolved structurally the same way living systems adapt over time. Material reuse also accelerated survival. Bricks and stones from collapsed sections were frequently recycled into nearby repairs, reducing transport time and cost. This meant damaged areas could be stabilized within weeks or months rather than years. Reused materials already proven durable were favored over untested alternatives. Ming military records describe regional repair depots positioned every few dozen kilometers. Fast rebuilding prevented small cracks from becoming permanent failures. Standardization made reinforcement scalable. Ming dynasties introduced uniform brick dimensions, roughly 40 by 20 by 10 centimeters, allowing rapid replacement without custom fitting. Mortar recipes were standardized as well, ensuring predictable strength and curing time. This modular approach meant any damaged segment could be repaired by any crew. Uniformity reduced structural weak points caused by mismatched materials. The wall became repairable infrastructure rather than bespoke architecture. Reinforcement often followed seismic damage rather than preempting it. Earthquakes exposed which sections failed under stress, guiding future upgrades. Later builders thickened parapets, added internal fill, or reinforced joints where cracks repeatedly appeared. This process mirrors modern post-earthquake retrofitting strategies. Instead of resisting change, The wall absorbed lessons from every disaster. Destruction became a design tool. What survives today is therefore not a single historical moment, but the end result of relentless iteration. Sections that could not be maintained disappeared, while maintainable designs multiplied. The wall did not outlast centuries by being perfect at birth. It survived by being endlessly corrected. In that sense, the Great Wall is less a monument and more a process frozen in stone. After cycles of rebuilding refined the structure, earthquakes became the ultimate stress test. Large portions of the Great Wall of China sit near active faults in northern China, a region that has recorded dozens of magnitude 6 to 8 earthquakes over the last 2 millennia. The 1303 Hongdong earthquake, almost equal to M8, and the 1556 Shaanxi earthquake, almost equal to M8, devastated cities, killing hundreds of thousands. Contemporary records describe city walls collapsing while nearby Great Wall sections suffered partial damage rather than total failure. This uneven outcome revealed how differently the wall responded to seismic forces. Earthquakes did not spare the wall, but they did not erase it either. During earthquakes, damage followed predictable patterns rather than random collapse. Cracks usually appeared at parapets, crenellations, and outer brick facings rather than at the core. Core fills made of rammed earth or rubble often remained intact even when outer layers failed. Structural surveys show that in many sections, over 70% of the internal mass remained stable after major seismic events. This meant walls lost surface integrity but kept load-bearing capacity. Earthquakes peeled the wall instead of snapping it. Another critical factor was how seismic energy entered the structure. Earthquakes generate vertical and horizontal waves, but walls anchored into bedrock experienced reduced horizontal acceleration. Measurements from modern analog sites show bedrock foundations can reduce lateral motion by up to 40% compared to soft soil. Many Great Wall sections were effectively pinned to rock, limiting sliding and overturning. Instead of moving as a whole, the wall absorbed energy in small localized motions. This kept failures contained. Earthquakes also revealed why segmentation mattered in real conditions. When tremors exceeded tolerance, individual segments collapsed without triggering neighboring sections. Watchtowers and gates acted as mass breaks, stopping crack propagation. Historical earthquake accounts often mention collapsed towers rather than entire wall lines falling. This indicates localized failure zones rather than system-wide collapse. The wall failed in pieces so the whole could survive. Post-earthquake behavior mattered as much as the quake itself. Cracks exposed walls to rain infiltration, freeze, thaw cycles, and erosion. Ming-era repair logs show that damaged sections were often reinforced within months, sometimes weeks. Quick sealing prevented microcracks from expanding into structural fractures. Earthquakes weakened the wall, but rapid response prevented delayed collapse. Adaptation continued after the shaking stopped. Over centuries, repeated earthquakes acted like a brutal selection process. Designs that failed repeatedly were abandoned, while those that survived were replicated. This created a wall increasingly tuned to its seismic environment. The Great Wall did not resist earthquakes through strength alone. It survived by being tested, damaged, repaired, and improved again and again. Adaptation, not endurance, was the real defense. After earthquakes tested the wall structure, human invasion tested its purpose. The Great Wall of China was never meant to be an impenetrable barrier stretching unbroken across the land. Historical records show that major invading forces, including Xiongnu, Khitan, Jurchen, and later Mongol armies, rarely attempted to dismantle long wall sections. Tearing down masonry 5 to 7 meters thick would have taken weeks, cost manpower, and offered no immediate strategic reward. Instead, invaders targeted gates, mountain passes, and political weaknesses inside China. The wall survived because attackers treated it as an obstacle to bypass, not a structure to erase. Military logic favored speed over destruction. Invasion forces depended on rapid movement to avoid supply shortages and counterattacks. Historical campaigns show armies covering 30 to 50 kilometers per day, making prolonged demolition impractical. Breaching a single fortified gate or negotiating passage was far faster than dismantling hundreds of meters of wall. As a result, most wall damage from warfare was localized near gates and choke points. Large uninterrupted stretches were often left untouched. The wall's elevation and terrain also discouraged direct assault. Many sections sit atop ridges or cliffs where siege engines could not be deployed effectively. Ladders, towers, and rams were useless against walls perched tens of meters above steep slopes. Attacking uphill under missile fire dramatically increased casualties. Invaders preferred flatter routes where mobility and numbers mattered more. Geography once again reduced direct structural damage. Even when invaders successfully crossed the wall, destruction was rarely systematic. The Mongol conquest of the 13th century bypassed many wall sections entirely by exploiting internal political fractures. Once inside, Mongol forces focused on cities, supply centers, and ruling elites rather than fortifications behind them. Wall sections behind advancing armies lost strategic value and were ignored. Survival came from becoming irrelevant, not invincible. Another overlooked factor was reuse rather than destruction. Some invaders occupied and garrisoned existing wall sections instead of tearing them down. The Jin and Yuan dynasties maintained and modified parts of the wall for their own defense. Destroying useful infrastructure made little sense when it could be repurposed. Occupation preserved structure where annihilation would not. Ultimately, the wall survived invasions because it was rarely the primary target. Warfare aimed at control, not demolition. Earthquakes damaged the wall more consistently than armies ever did. By being too large, too slow to destroy, and too often bypassed, the wall avoided systematic eradication. What was meant to stop enemies instead outlasted them. Survival came from strategic irrelevance. After invasions failed to erase it, the next key to survival was variation across time. The Great Wall of China is not a single wall but a collection of walls built by different dynasties over nearly 2,000 years. Qin and Han sections relied mostly on rammed earth, while northern dynasties mixed stone and earth depending on terrain. The Ming dynasty shifted heavily to fired brick and stone in high-risk zones. These differences produced wildly different survival outcomes. What remains today is heavily biased toward the strongest designs. Qin dynasty walls, built around 221 to 206 BCE, were fast and utilitarian. Rammed earth was ideal for speed and scale but vulnerable to long-term erosion once maintenance stopped. Many Qin sections eroded completely within a few centuries, especially in arid or flood-prone regions. Han dynasty walls improved slightly by incorporating gravel and reed layers. However, without protective facings, most Han walls degraded once garrisons withdrew. Their disappearance was gradual, not sudden. Northern dynasties experimented with stone in mountainous regions where earth was scarce. Stone walls resisted erosion far better but performed poorly in earthquakes if not layered. Many collapsed catastrophically when rigid masonry cracked. This revealed a trade-off between durability and seismic flexibility. Regions with frequent earthquakes punished overly rigid designs. Survival required balance, not just strength. The Ming dynasty, 1368 to 1644, produced the most durable surviving sections. Builders used fired bricks, sticky rice mortar, thick stone bases, and standardized dimensions. Ming walls averaged 6 to 8 meters high with bases up to 7 meters wide, and were often reinforced with internal rubble cores. Archaeological surveys show Ming sections account for over 60% of visible wall remains today. Their survival reflects accumulated engineering lessons. This was the wall at its evolutionary peak. Geography amplified these differences. Earthen walls on plains vanished fastest, while brick and stone walls on ridges endured. This created a survival bias where only certain dynasties appear successful today. The wall we see is not representative of the entire project. It is the filtered outcome of centuries of failure. History erased the weak and preserved the adaptable. In the end, the Great Wall's survival is uneven because its construction was uneven. Different dynasties solved different problems with different tools. Time, earthquakes, and invasions selected the best answers. What stands today is not the Great Wall as it was built. It is the Great Wall as it survived. After seeing how materials, geography, systems, and adaptation shape survival, the final explanation is comparative. The Great Wall of China outlasted many ancient wonders because it was not built as a single ceremonial structure. Monuments like temples, palaces, and statues concentrated meaning, resources, and fragility in one location. When earthquakes, floods, or invasions struck, failure was total. The Great Wall, by contrast, spread risk across thousands of kilometers. No single disaster could erase it all. Scale alone was not enough. Function mattered. Many ancient wonders lost purpose once the civilizations that built them collapsed. Without function, maintenance stopped, and decay accelerated. The Great Wall retained military and logistical relevance for centuries, even as dynasties changed. Active use meant active repair, garrisons, and material supply chains. Utility delayed ruin. Another difference was tolerance for damage. Ancient monuments were designed for visual perfection and symbolic permanence. Once cracked or partially destroyed, they were often abandoned rather than repaired. The Great Wall accepted imperfection as normal. Cracks, collapses, and reroutes were expected outcomes, not failures. This mindset turned damage into maintenance instead of abandonment. The wall also benefited from redundancy rather than uniqueness. Ancient wonders were singular objects with no backups. The Great Wall repeated its design thousands of times across terrain. Losing one tower or segment did not reduce overall function. Redundancy absorbed loss without systemic collapse. Survival favored systems over icons. Time itself played a different role. Many monuments faced concentrated destruction over short periods. The Great Wall experienced slow, distributed damage over centuries, allowing adaptation between events. Earthquakes, erosion, and warfare arrived in intervals, not all at once. This pacing allowed learning, rebuilding, and improvement. Survival unfolded incrementally. In the end, the Great Wall survived because it behaved less like architecture and more like infrastructure. It was flexible, redundant, repairable, and constantly revised. Other wonders sought timeless perfection and shattered when time arrived. The wall accepted change and endured it. What still stands is not defiance of history. It is cooperation with it.